Have you ever felt your ears pop while diving into a swimming pool? Or noticed how water gushes out more forcefully from the bottom of a tank? That's liquid pressure at work. Hi everyone. In this session, we'll dive, quite literally, into the concept of pressure exerted by a liquid column. Liquids exert pressure on any surface they're in contact with, on the bottom and the walls of a container. But here's the key idea: this pressure increases with depth. The deeper you go, the more liquid is above you, and the greater the force it exerts. Now, this pressure isn't just random, it follows a clear mathematical rule: P equals H times rho times G, where P is pressure in pascals, H is the depth in meters, rho is the density of the liquid in kilograms per cubic meter, and G is acceleration due to gravity in meters per second squared. Let's explore where this formula comes from. Let's derive that equation step by step. Imagine a vertical column of liquid. Let's say the liquid has height h, cross-sectional area A, and density ρ. Now, the volume of this column is a times h. So the mass m of the liquid is ρ times A times h. Next, we calculate the force, which is the weight of this liquid. F equals m into g, so F equals ρ times A times h times g. Now, what is pressure? It's force divided by area. So, P equals F over A, which becomes P equals open bracket ρ times A times h times g close bracket divided by A. The A cancels out and we are left with P equals h times ρ times g. And that's the formula that governs pressure at a depth in a liquid. Now let's break this formula down to understand what affects liquid pressure. First, depth h. The deeper you go in a fluid, the more weight is pressing down, so pressure increases. Second, density ρ. Thicker liquids like honey exert more pressure than lighter ones like kerosene. Third, gravitational acceleration g. If you're on the moon, where gravity is lower, the pressure at the same depth would be less. And here's something really interesting: the shape or volume of the container doesn't matter. Only the height of the liquid column counts. As shown in the diagram, even if the container is wide, narrow, or oddly shaped, pressure at the same depth is equal. That's the elegance of physics: simple rules, universal truth. So, how do we verify this practically? Let's take a classic experiment: a can with small holes at different heights. When filled with water, the streams from lower holes shoot out farther than those from the top. Why? Because pressure is greater at the bottom. It's proof that pressure increases with depth. There's also the hydrostatic paradox, where differently shaped containers filled to the same height exert equal pressure at the bottom. This surprises many students, but again, it confirms that only depth matters, not shape. And then there's Pascal's barrel experiment, a narrow tube connected to a barrel. Just a little water in the tube caused the barrel to burst due to the high pressure created at the base. As you can see in the diagrams, these visual proofs bring formulas to life. Now let's see how this concept helps us in the real world. Dams are thicker at the bottom because the pressure from the stored water is highest at the base. Engineers use the formula P equals H times ρ times G to design safe and stable structures. Water tanks are placed on rooftops so that gravity helps build pressure. That's why the higher your tank, the stronger your water flow. Divers and submarines use equipment specially designed to withstand the massive pressure at deep underwater levels. Even deep-sea creatures have evolved to survive the intense liquid pressure where sunlight never reaches. So this isn't just theory, it's how we manage water, design cities, and explore the oceans. Let's solidify our understanding with an example. Problem: Calculate the pressure at a depth of 4 meters in water. We are given H equals 4 meters, rho equals 1000 kilograms per cubic meter, G equals 9.8 meters per second squared. We'll use P equals H times rho times G. Now substitute P equals 4 times 1000 times 9.8. That gives us P equals 39,200 pascals. So the pressure at 4 meters below the water surface is 39,200 pascals. That's how powerful even a few meters of water can be. Let's quickly revise what we've learned today. Liquids exert pressure that increases with depth. The pressure depends on the height of the liquid column, the density of the liquid, and the value of gravity. And remember the formula, P equals H times rho times G. This pressure acts equally in all directions at a given depth and is independent of the shape of the container. We verified it through experiments and saw how it's applied in dams, buildings, scuba gear, and water systems. So the next time you turn on a tap, remember, it's physics and gravity working together behind the scenes. I hope this session helped you understand how liquid pressure works from tanks to the deepest trenches. See you in the next video with another fascinating concept in physics.